All right, so we'll get started. So today, first of all, thanks to everybody who's here in person. And if you're here on Zoom, then you can use the chat if you have any questions. Thanks for joining us. I saw you on Zoom earlier. Today we're continuing our discussion of compressible flow. Right, this is the last chapter that we have to cover, and we're going to in today's class learn how to solve an important type of problem in compressible flow, which you're then going to see on the homework, which I expect most of you are going to be doing next week. We're working towards solving two kinds of problems in compressible flow. So the first of these are what are often called nozzle problems, and the second is what's often called a shock problem. The basic idea of what we're trying to do here is figure out, for example, if we have a nozzle, or this would be like internal flow, like a compressible internal flow problem. We'll often want to know, for example, the values of the velocity, the temperature, the pressure at location 2. Based on, for example, conditions maybe far upstream or conditions at some other point within this system. And so we're going to look at, we're going to develop mostly today a set of expressions that allows us to relate the velocity, temperature, pressure, all the different flow variables within internal flow, within internal compressible flow, as a function of the area of that that the flow is moving through. We're also going to then later, starting on Monday, right? So after Thanksgiving break, we will apply the same kind of idea to shock problems, where again, generally we're going to be asking, like, what is the temperature, pressure, velocity behind the shock as a function of what was happening in front of the shock. Okay, so we're generally going to be moving like from point to point, and so this is basically like a control volume analysis is what we're doing. Yep.
Would the nozzle situations apply to the same kind of leak in a pipe system?
Yeah. So the question is, would the nozzle system apply? Say we had a leak in a pipe system. What are you getting at? What do you mean if we have a leak in a pipe system?
So like, if you had like say you had like a pipe that was like highly compressed, wall pressure, and something came in and poked a hole.
Yeah, and so the question is, if we have a pipe and something came in and poked a hole, repeating for Zoom, then would that be something like a nozzle situation? Yes, that would definitely be something like a nozzle. Okay. And we're actually going to talk about that case, maybe end of day today, probably beginning of Monday, of what happens if we have basically a hole in a compressed air tank or something, or in for example a pipe. So yeah, so we will talk about that. But this also, it doesn't have to necessarily be, to do this kind of analysis, you don't have to necessarily be venting to atmosphere. So in general, this, when we call it a nozzle type problem, is any problem, any compressible flow problem where we have changing area. So so we'll look at, and we'll see some other examples. Like if you have a partially closed valve, you could use the same kind of analysis here. So to get there, we're going to be using balance equations, right? So as I mentioned last time, this is primarily like a chapter 3 type approach, but now to compressible flow. We're going to use our mass momentum balance equations, which we've been using up till now, plus energy balance and equation of state, because the temperature varies, right? Therefore, we need to track energy balance and energy balance, and we need to keep track of the internal energy of the fluid. That's really what's new here. The equation of state is what's going to allow us to couple changes in, for example, pressure to changes in density, pressure and temperature to density. So we have thus far been considering isentropic flow of a perfect gas. So if you remember, before we discussed the speed of sound and we developed an expression for the speed of sound, we wrote down these expressions here in the top right, relating differences in pressure to differences in temperature and differences in density. And in order to develop those equations, we assumed perfect gas, right? So ideal gas with constant specific heat. And we also assumed isentropic flow, right? So no entropy change no entropy change in that flow. And so if we also assume adiabatic, we assume that there's no heating, then we can actually greatly simplify our analysis, right? So we're going to say that there's no heat transfer and no change in entropy. Temperature can still change, right? So as we compress or expand the gas, we can have a change in temperature. So temperature is not constant, even though we're making this adiabatic assumption. But with these two assumptions, we can greatly simplify our analysis. So we're going to start with an energy balance. In this case, we're looking at flow past an insulated wall. And this looks a little bit like our standard energy balance, but note that we're keeping in the internal energy, because again, the temperature changes, so the internal energy of the fluid will change within this flow. So if we ignore gravity, right, so we're going to drop out those GZ terms, and we're going to ignore, right, we said it was adiabatic, so we're ignoring heating, and we're ignoring any viscous work. We're going to say that we're generally in compressible flow, at least in this class, our treatment of compressible flow, we're going to be considering flow outside of any boundary layers. So even when we're looking at flow inside of a chamber, we're going to be assuming that the effects of the wall are small. And then we're left with this expression here. So this is, a little bit reminiscent of Bernoulli, except it wrapped up in this H is not only pressure, right? Not only the potential for us to use pressure to do work, but also the internal energy of the fluid. So, yeah, sure. So on this diagram here, we're looking at, so this is showing the velocity, and this is the stagnation enthalpy. So we haven't actually discussed what stagnation enthalpy is yet. So yeah, but we'll talk about stagnation enthalpy in a second. Yep.
We're going to assume compressible, so we talk about the physics work term, but if we're dealing with speed, doesn't that not apply anymore?
Sorry, doesn't what not apply? The
you can assume incompressible. Shouldn't they be compressible if we... Sorry,
did I say we're assuming incompressible? We are not. We are definitely not assuming incompressible. Okay. Yeah. If I said that, I'm sorry. We're assuming adiabatic, yeah, which means this heat term goes away. Yeah, sorry, we're definitely not assuming incompressible. If I said that, I apologize. That was wrong. Okay. Definitely not. We're not making that assumption in this chapter. So okay, so we're left with this expression, right, relating our enthalpies and velocities at point 1 and point 2. So now imagine if we take this V and we take the velocity and we allow the flow to slow down without heating and without any change in entropy, right? So in ideal situations, slow the flow down to 0, then that will give us the maximum enthalpy of the flow, the maximum possible enthalpy. And we'll call that H naught. This H naught is called the stagnation enthalpy. So it's like the enthalpy of the flow, the pressure and internal energy of the flow, if we decelerate it all the way to 0 isentropically. For non-perfect gases, we need to use steam or gas tables, right? If we want to treat, if we want to really go any further than this. But for perfect gas, we have H is equal to Cp times T. And so we can write out this expression here. We can expand this expression as Cpt plus 1/2 V squared is Cp times T naught. Again, bring in some thermo. So we're going to start there, right? So again, it's telling us the enthalpy at some point in the fluid plus basically the kinetic energy per unit mass within the fluid, that 1/2 v squared, is equal to Cp, the stagnation enthalpy, in this case Cpt naught. And now one thing that we can do is we can actually take this expression and non-dimensionalize it, right? So we can, we're playing the same tricks over and over again. In this case, we're non-dimensionalizing this expression, but basically dividing through by Cpt, right? And so now we have 1 plus v squared over 2 Cpt is T naught over T. And we'll note that we can write out CPT in terms of what we know from our perfect gas assumption. So CPT is a squared over k minus 1. A is the speed of sound. Yep.
Is R here the weird R again?
R here is the, yes. So in this, in our treatment here, R is going to be the individual gas constant, not the universal gas constant, right? So this is again the individual gas constant. So basically what we're doing here is we're relating this Cp times T to the speed of sound, A, within the fluid. And so what this is going to give us, sorry, my animation is a little bit messed up. So we're going to end up with this expression for the temperature within our fluid relative to the stagnation temperature based on Mach number. So based on the velocity relative to the speed of sound. So what this tells us is that if we know at a given point within the flow, if we know the Mach number at that point, then we also, from this relationship here, know the temperature relative to the stagnation temperature. Okay. So if our Mach number is 5, then T over T naught is about 1/6. Okay. Yeah. Is stagnation enthalpy ignoring the movement of gas molecules? So we have made the continuum assumption here, right? So we are treating the fluid as a continuum, meaning that the size of our system is still much larger than the space between individual gas molecules. Okay, but in a sense, like the movement of individual gas molecules is how we get pressure, right? You know, thermodynamics, like that's where pressure comes from. So we're not ignoring it. We're just it's lumped into our thermodynamic equations of state and for our system. Does that make sense?
Yeah. So like T naught is not absolute zero.
Oh, sorry. T naught is not absolute zero. Yeah. So T naught is like, let's say we have, and we'll see this when we're going to develop some more expressions like this relating local flow properties to stagnation conditions. And then we'll be using this to solve problems. But T naught is like the temperature. Like, let's say I have a compressed gas cylinder sitting somewhere, right? The pressure inside of, I have some given pressure inside that cylinder, and that cylinder is at some temperature, and flow there is at stagnation, right? Flow is not moving, so it's at some T naught temperature, right? Let's say it's room temperature or something inside that cylinder. And now if I pass the gas from that compressed cylinder through some set of valves and piping, right? And I know, let's say I know the Mach number at some point downstream, in this big network, right? In this network of piping and tubing and whatever. If I know the Mach number at some point downstream, this is telling me what the temperature at that point downstream would be. Alternatively, if I knew the temperature, I could figure out the Mach number. Okay, does that make sense? So this is not absolute zero. This is, or actually this thing would be undefined, right? This is not absolute zero. This is the T naught here is the temperature at stagnation, or the temperature if we either isentropically decelerate to zero, or if we isentropically accelerate from 0 up to whatever our current velocity is. That makes sense? Okay, yep. So Yeah, so the question is, can you explain how those two things are equivalent, accelerating or decelerating? So we've ignored any viscous work. We've said that there's no heating, right? And then we've basically done an energy balance between some point, we'll call it point 0, some stagnation point, and some other point, I don't know, point 1, where we have some temperature and some Mach number, right? That energy balance works in either direction, right? So we can either go from 0 to 1, from stagnation to whatever condition we have, or whatever, wherever our Mach number is, let's say 5, right? So we can go from 0 to 1, we can accelerate to get there, or we could decelerate the flow to go from Mach number 5 down to 1. And as long as we do so isentropically, right, without heating it, then this will tell us the ratio of, for example, the temperature to stagnation temperature. Does that make sense? Okay. Because but that basically just comes from the fact that, again, we've ignored viscous work, right? That would make it irreversible, right? And we've just basically done an energy balance. So we didn't say which direction it necessarily had to go in. Yep.
So we're also doing essentially like
no, we haven't said that the Mach number is 1 at stagnation. We're going to talk about when Mach number is equal to 1. That's a special condition in compressible flow. At stagnation, the velocity is 0, right? So the Mach number is really 0 at stagnation, right? Because if V is 0 and our Mach number is V over A, right, then Mach number at stagnation is 0. Okay. Yeah, Mach number 1 is going to be a very special thing in compressible flow. And that's where things are going to get weird if they haven't already. Okay. Any other questions on this? Because we're now going to basically extend this analysis to our other variables, right? So we can, we can use the equation of a perfect gas in order to relate temperature to pressure, temperature to density, right? And so that's what we're going to do next. But does this concept make sense? Okay. And again, so one reason why you have a homework this week is to get some practice with this kind of thing, okay, in solving problems. We're going to talk about how to, or walk through how to solve problems with this today, or discuss how you'd use this to start solving some problems today. And that's really going to be one of the key things on the homework this week. So I encourage you to look at it, even if you don't turn it in for a grade, because you have, so many homeworks done already. Okay, so one other thing to note here is that the speed of sound, as we change, right? So speed of sound is a function of temperature, right? So for example, speed of sound in meters per second is about 20 times the square root of the temperature in Kelvin in air. So speed of sound is a strong function of temperature. So if we have flow through our system where the temperature is changing, then that means that the local speed of sound is also changing. Okay. So, one key concept here is that speed of sound is not a fixed number. You can think of it as like a local flow condition in compressible flow. Okay, and Mach number describes the local flow condition, not the speed relative to some absolute number. Speed of sound is not like speed of light in a vacuum or something. Okay. It does change within the system. And one way to think of it is that since speed of sound is a function of temperature, and temperature changes, right? As you compress and expand a fluid, a compressible fluid, the temperature changes, right? And therefore the speed of sound, the temperature changes, and therefore the speed of sound changes. Okay. So we can therefore relate the local speed of sound, A, right, at some point within our system, we can relate the speed of sound at that point to the speed of sound at the stagnation condition. And we can find it with this expression here. It's plotted here is this A over A naught curve, right? Here is T over T naught, what we just discussed on the previous slide. Right, so again, this is because Speed of sound goes as about the square root of temperature. It varies with the square root of temperature, and the temperature can vary pretty dramatically within a compressible flow system. And just to reemphasize, so if we say consider flow at Mach number equal to 5, we mean 5 times the local speed of sound. Okay, so relative to the speed to local A, relative to the local speed of sound. That makes sense? Yeah. So the speed of sound relation to temperature that we developed was for a perfect gas, but we did not make the adiabatic isentropic assumption to get there. So our speed of sound relation, right, which gave us this, we did not make the isentropic assumption, isentropic adiabatic assumption to get this. But this expression, in order to get here, we did have to assume isentropic and adiabatic. Does that answer your question? Oh, this we developed from the perfect gas relationship. So this is true for a perfect gas. For this, so to get here, we assume perfect gas. Yeah, and then to get to, so the question was, which piece of this assumes adiabatic and isentropic? So to get here, we assume perfect gas. To get here, we assumed adiabatic and isentropic. Okay. Yep. Yeah. So the question is, what a perfect gas is ideal gas with constant specific heats, and that's correct. Okay. Yeah. So an ideal gas is not necessarily a perfect gas. Yep. Yeah. So we make the further assumption that we have constant specific heats. Okay. So that gives us, for example, a constant K, right? Which we're relying on pretty heavily here. Any other questions? Yeah. That's A. So local A is A. A naught, what is A naught? Can you tell me what A naught is? Speed of sound of stagnation. Yep. So if we have flow from a big compressed gas cylinder or something that's at 0 velocity, and we're moving isentropically away from that, A naught is the speed of sound within that cylinder. Okay. And so as we move away from that, right, through a system, like through a nozzle, for example, the temperature will vary, right? The pressure is changing, the density is changing. We're going to talk about that. And so the temperature will vary, meaning that the local speed of sound as we move through a nozzle will change. Okay. Yep.
So when we're talking about say that we're it's talking about like relative to the speed of sound around the plane.
Yeah. So the question is, when we say a plane is flying at Mach 5, what are we referring to? So, in that case, we would. It's sort of analogous to in external flow and when we were talking about Reynolds number, right? If you wanted to say what is the Reynolds number for flow around the plane, you would use the velocity of the plane, the velocity of the at which the plane is moving through the air, relative, and the overall length of the plane, right? To come up with an overall Reynolds number, right? So similarly, if you wanted to describe an overall Mach number for that plane, right? You would take the velocity of the plane relative to basically the stagnation Mach number, right? Or the Mach number in the atmosphere, right? Or sorry, the speed of sound in the atmosphere, far away from the plane.
Okay, so internal flow, the Mach number relative to
But in external flows, right? If we define, if this is an airplane now, you can't really see, but if this is an airplane now, moving through the air, so we said we could define an overall Reynolds number would be like the velocity of this and like its length scale or something, right? But we know in external flows that the boundary layer depends on the local Reynolds number, right? Reynolds number based on distance, say, away from the leading edge, right? So for our analysis to figure out what's going on for flow around airplane or bottle, whatever, we define Reynolds number based on X, and that becomes a flow variable, like a local flow variable, right? So same thing would apply for Mach number. So we could define an overall Mach number, like the velocity of this thing relative to the speed of sound in the atmosphere, right? But if we want to actually really understand what's going on, and like maybe there's a shock wave forming at some point, like we saw in some of the visualizations yesterday on Monday, then we would have to know the local Mach number at each point as we move around. Okay.
So basically, fluids is really hard.
Basically, fluids is really hard. I mean, yeah. So there are many things. So the comment was that there are many things to take into account. There are many things to take into account. We're looking at sort of select problems, for example, in compressible flow, select problems in compressible flow, and trying to provide a way for you to kind of work your way stepwise through them, right? To try to help with some of the fact that there's so many things to consider. Okay. But yeah, there are quite a few things to consider, and we're barely scratching the surface of compressible flow in this class. Yeah. Okay. Any other questions? Okay. So now for isentropic steady adiabatic flow, we can use the isentropic relations to write, to solve for example, our pressures and densities as a function of stagnation pressures and densities as well. So we have P naught over P is T naught over T to the K over K minus 1 power, right? We developed this from our perfect gas relations. We from our isentropic perfect gas relation, and we can combine that with our adiabatic expression to develop this. We can do the same thing for density, right? And develop this expression here, which is plotted again on this plot here to the right. This is rho over rho naught, and this is P over P naught. So one thing I want to note here, like this looks complicated, but really, like let's say if we're considering air, we know K, or whatever gas we have, right? We know K. The only other thing that appears in this expression, even though it looks complicated algebraically, the only other thing that appears in this expression is Mach number, right? This is, maybe takes a little bit of time to plug into a calculator, but as long as you know local Mach number, this actually can tell you quite a bit about the flow, okay? It looks complicated, but it's actually fairly simple in the fact, in the sense that there's really only one variable here, right? That we have to consider, as long as we can use these relationships. So again, here, P naught is stagnation pressure, rho naught is stagnation density. I'll put this up before, right? So again, that would be pressure if we isentropically, adiabatically decelerate the flow to 0, and density, right, under the same conditions. Pressure and density of fluid is brought isentropically to rest, or the condition at rest before accelerating isentropically. If it is non-isentropic, so if the entropy varies, then P naught and rho naught will vary with position in the flow. So we're going to consider when we're considering flow through a shock wave, that is, a shock wave is non-isentropic, and therefore we're going to have these P naught and rho naught are going to then become variables of our local conditions. But we'll get there. We'll get there soon. Okay. Yeah, so the note being made here, actually, I think, Nathan, I do need to correct myself. Our relationship for T over T naught, that was just assuming adiabatic. So we actually had not applied the isentropic assumption to get there. But whereas to get to our expressions for rho and P, those were for both adiabatic and isentropic. So our expression for, again, for T over T naught, that was only assuming adiabatic. It's only assuming no heating, not assuming isentropic. Okay, meaning that we're going to be able to use these relationships when we get back to flow through a shock wave, for example, where it's not isentropic, but these expressions are only going to be appropriate when we have isentropic flow. Okay, so we're also going to be working with air, right, to solve problems. And so we can take all of those Ks and factors of K and manipulations of K out of or we can just write out numerically what those things are. And then we'll end up with these expressions, which are, again, make it really clear that in each one of these expressions, the temperature, the pressure, and the density relative to stagnation is just a function of Mach number, right? So again, that's the only variable that appears in these expressions. And so this also means we can invert these and solve for Mach number, right? So unlike in our internal flow example, we couldn't always solve for things on one side or the other. Again, these, have these complicated looking factors, but we can actually manipulate them pretty readily. And if we knew temperature relative to stagnation, we can figure out what the Mach number is, right? And so on. All right, so we've been alluding to this throughout the class, but now we're kind of ready to start applying this to a real application. And this is to look at compressible flow with area changes. So, what happens, so a big question here is what happens if I have flow through some shape where the area varies, right? So, some kind of a nozzle shape, right, like a rocket nozzle, Venturi, or even just a system with, varying, any kind of variation in size, right, in internal area. So what happens when we have flow through such a shape? We can now analyze with these kinds of methods. So I just want to take a second here and remember how we handle this for the incompressible flow case. So if the flow is incompressible, we started with mass conservation. This still holds for compressible flow, right? M.1 is equal to M.2, right? So between conditions 1 and 2 within this system. This still holds if we have compressible flow. We can expand that out, and we said rho 1 A1 V1 is rho 2 A2 V2. This still holds for compressible flow. But when we had incompressible flow, we had this special case of rho 1 is rho 2 is constant, and therefore we said this, right? Again, for incompressible flow, the densities dropped out, right? So A1 V1 was A2 V2. So for incompressible flow, if the area went up, the velocity had to go down, right? So if we're moving from this point here to this point here in incompressible flow, the area is going up, so we know the flow was slowing down. In compressible flow, this is not always true, okay? So in compressible flow, we're stuck with this expression here, right? Because density varies in compressible flow. And so under some conditions, and we're going to talk about what those conditions are, but under some conditions, if we increase the area, we can actually get the flow to go faster. Okay, so under some conditions in compressible flow, as we move from some narrow region to a wider region, the flow can actually speed up. Okay, so this is a big difference here. So let's try to look at that. So if we have steady one-dimensional flow, we know we can write rho VA is equal to m dot is equal to a constant, right? So we're going through some system. We're moving through that system, right, with X as our variable, moving through the system with variable area. This holds, right? This expression of mass conservation holds. Now, rho is a function of our position through the system, right? Density can vary as the flow varies, right? Area varies because that's how we set up the problem. We said we're moving through a nozzle with variable area. Velocity varies. We're used to that, right? From incompressible flow. But now density can also vary as we move through the system. So from this expression, this expression implies this differential relationship between changes in density, changes in velocity, and changes in area. This is developed a little bit further in your text if you want to go further from that first line to that second line. But now we can combine this with the momentum balance, neglecting friction, and the definition of the speed of sound to relate essentially our density to pressure. This is rho, this is P. Okay, for sitting at the back, maybe that's hard to see, but this is rho and this is P. And from our frictionless momentum expression, again, this is P, this is rho. I need to redo those in LaTeX, I think. And the end result here is this expression here. So this is dV over V is dA over A, where 1 over Mach number squared minus 1. Okay, so this tells us how the velocity changes within our system are related to area changes within the system. So this thing here is a little bit strange. So let's say if we have Mach number is really low, if this thing is basically 0, then this tells us, right? So if Mach number is basically 0, this thing drops out, this becomes 1 over 1, right? So in the incompressible case, this tells us dV over dV is equal to dA over A, meaning any changes in velocity are balanced out by changes, or any changes in area result in change in velocity in the direction that in the way that we expect, right? So if we, our velocity will increase if our area decreases. Sorry, this becomes a -1. Sorry, 1 over -1, right? Meaning that if area goes down, the velocity goes up. If area goes up, the velocity goes down. Sorry about that. This becomes a -1. But in the compressible case, Mach number is not equal to 0, right? And so this thing can cause some kind of strange behaviors. And I say this can be weird if you're thinking about subsonic flow, right? So if you're still in that subsonic incompressible flow mentality, this can give some weird behavior. Because if we look at this thing, if our Mach number is less than 1, then right, if our Mach number is less than 1, then this Mach number squared here is going to be less than 1. This whole thing here is going to be negative, right? And that means that as the area goes up, the speed goes down, and vice versa. So this kind of makes sense from our incompressible flow thinking. But if the Mach number is greater than 1, then this thing flips signs. This becomes positive, right? This denominator here becomes positive instead of negative. And so this means that if the area increases, if dA is positive, then dV is positive. The speed increases, the velocity increases. Okay, now that's weird, right? From a incompressible flow kind of thinking. But this can happen in compressible flow. So this is one way to think about what's happening here, or to kind of try to convince yourself that what's happening here makes some sense. Is that if we're in this condition of Mach number greater than 1, then as area increases, density is decreasing, right? So remember, what's not written here is density. We've used our speed of sound definition and some results from momentum balance in order to basically drop or drop the density out of this expression, right? To factor density out of this expression, but it's still there in this Mach number relation. One way to think of this is that if Mach number is greater than 1, as our area increases, density decreases faster than the velocity. And so the velocity has to increase in order to maintain mass flow rate. So when Mach number is greater than 1, basically the density changes overwhelm the velocity changes. And so we end up with this kind of reverse sign here. A little bit more information, a little bit more discussion of this address here. Okay, so yeah, one thing that I haven't said, it's like what happens? So if Mach number is equal to 1, right? We have a divide by 0 problem, right? We have something weird happening here. So this is maybe even more strange. So what happens when Mach number is equal to 1? Okay, so I said previously that Mach number equal to 1 is going to be a very special case in compressible flow. This is where we're getting into what that special case is. So again, just let's just look at cases of Mach number less than 1 or greater than 1. So less than 1, we're going to say, if Mach number is less than 1, we're going to say we're subsonic, right? We're less than the speed of sound, we're subsonic. And there, the relationship between velocity and area changes goes in the direction that we expect from incompressible flow. Okay. Now, when we have compressible flow, we can't just say, even if we're subsonic, we can't just say V1 A1 is equal to V2 A2 because density is also changing. Okay, so make sure you're including density in your expressions of mass balance anytime we have compressible flow. But the direction, the sign of the change or of the relationship between velocity and area is kind of what we would expect when Mach number is less than 1. When Mach number is greater than 1, we're supersonic, right? We're greater than the sonic speed. And therefore, the relationship between velocity and area switches signs. But at Mach number equal to 1, this would imply infinite acceleration, right? It would imply that at Mach number equal to 1, the velocity would just go to infinity. We have a Millennium Prize problem or something, right? But since this is not possible, right, we cannot have infinite acceleration. So this expression actually tells us that the only place that we can have Mach number equal to 1 is when dA is 0. That's right. Yep. So the only way that we can have Mach number equal to 1 within a system with area changes is when dA is equal to 0. Okay. So we can only hit Mach number equal to 1 at a region of dA is equal to 0. So if I'm looking at this system here, right, we've been looking at this image now the past 2 classes. We look at the rate of change of area, right, with respect to x as we move through the system, right? As we're coming into this this nozzle, right, the area is getting smaller and smaller and smaller, right? So dA is negative here, right? Out here, dA is positive, right? area is getting bigger as we move up in x. But at this point right here, there's some condition where dA is equal to 0, where the area is not changing, right? Where we're switching from this decrease back to this increase. That is, in this system, what this relationship actually tells us is that this is the only place where Mach number can be equal to 1. Yes?
When you say it can be equal to 1, it doesn't mean it has to.
It doesn't have to be equal to 1. Yep. If we have the flow really, really slow, and actually, this would be an important part of solving these types of problems. Is first asking, does it ever get to Mach number equal to 1 in this system? I see some confused looks. But if, like, let's say we have air moving through the system. Actually, let's say we have water moving through the system, right? So we assume it's incompressible. So the speed is always less than Mach number 1, right? And therefore, we would never have a place where the Mach number is equal to 1, right, with water flow. Or it could be airflow that's really slow. And therefore, we never get to the point of Mach number equal to 1. But if Mach number is 1 anywhere within the system, it can only be at this location. Yeah. Sorry, what's that? That implies that dV is equal to 0 at that point. That's right. It does. Actually, sorry. No, this expression is undefined at that point. Yeah, sorry, it does not necessarily imply that dV is this expression is undefined. Yeah.
So to know that it gets to 1, we need to know the change in area.
Yeah, that's exactly it. I'll repeat that for the video. That's where we're going next. So actually, instead of repeating for the video, I'm gonna walk through how we know. So I can tell you that Mach number is 1 at this point. I'll tell you how I know that. This looks like we're taking flow from we have flow from some really large reservoir. It looks like what we're viewing experimentally here, where at some point out here the flow is at stagnation, where the velocity is 0, and therefore Mach number is 0 out here. Then the flow is moving through this shape, this nozzle shape, and downstream we have a shock wave. We'll see, but we can only have a shock wave when the flow has a Mach number greater than 1. We can only have a shock wave in supersonic flow. So I know here the Mach number is greater than 1. So that means the flow through this shape is going from Mach number less than 1 to Mach number greater than 1. So that means it has to pass through Mach number 1 at some point. And since the only place the Mach number can be 1 is when dA is equal to 0, we know that the Mach number is equal to 1 at this point. That makes sense? Yeah.
So we're not ever able to create a shock wave in cone.
So we're not able to ever create a shock wave in a cone if there's not a place of constant area. That's correct. Yeah. But we'll talk a lot more, quite a bit more about that. So if you're not following along right now, then we're going to talk quite a bit more about that. So to go supersonic, we need to accelerate the flow, meaning we need to have a local minimum, right? So a consequence of this we just talked through a little bit, but stated another way, is that if we ever want to make the flow supersonic, we need to go through some kind of a minimum, some kind of a local minimum area. And we call this the throat. So this kind of minimum area where we have dA is equal to 0, right? We have some local minimum. We call that location the throat. So we know that if we have supersonic flow out of a nozzle, then we know that Mach number was equal to 1 at the throat, at this point where dA was equal to 0. Any questions on that? We discussed it a little bit, but yeah, here. As the Mach number approaches 1, dA has to approach 0. That's correct. What is actually happening at the throat? So we're going to use our Mach number relations. Actually, on the next slide, we're going to start using the Mach number relations that we've developed. Those hold. Okay, so we can use those to figure out actually the density, the velocity, everything we need to know at this condition. Okay, yeah. If we plotted dV versus dA, would it look parabolic? Why do you say that? I have to look at that before I answer. Yeah. We will look at we're about to develop the tools that it would take to plot that. Actually, we're just about out of time. Okay, so that's a good point where we're going to have to end. So we're going to look at, so starting on Monday, so after Thanksgiving, we're going to look at perfect gas flow through a nozzle. But basically, just to give you a preview of where we're going, you know, these expressions here, for example, for air, like these are going to hold. So for example, if we want to know what's going on in the throat, we're going to plug in Mach number of equal to 1, right? And then we're going to be able to relate pressure to stagnation pressure, density to stagnation density, temperature to stagnation temperature. Okay, so we're going to be able to solve for everything that we need to know at the throat. Okay, from using these relationships, and that's where we're going on Monday. Okay, any other last questions before we break? Lots of questions. Yeah. Okay. All right. Well, then have a happy Thanksgiving, everyone. Thanks everyone who was here in person and online. And I will see you all on Monday.